Hello, in this video I'm going to describe the Arakawa grids, which can be used for modelling the shallow water equations in 2 dimensions and can also be used for modelling 3-dimensional Euler equations and Navier-Stokes equations, except some other approximations need to be made for the variations in the vertical direction. So just thinking about 2 dimensions, the Arakawa grids are A to E, and it's all about storing components of velocity and height at different places. So in 2 dimensions, there are a lot of possibilities for where you can store components of velocity and h, the height. So the most obvious thing is store everything at the same place, at the centre of a grid box. You've got both 2 components of velocity and the height all at the same place. It's an A grid. A B grid, you've got the velocity staggered from h, staggered in the x direction and in the y direction, and you've got both components of the velocity stored at the same place. A C grid has got h in the centre of a grid box, and the x direction velocity is stored staggered in the x direction, and the y component of the velocity v is staggered in the y direction. The D grid is the other way round. It's got the u component of the velocity staggered in the y direction and the v component staggered in the x direction. And finally the E grid, well really the E grid with u and v stored at the same location, staggered from h, it's just a version of the B grid but rotated by 45 degrees. So it's not really very distinct from the B grid. So what are the properties of these grids when you use them for modelling the shallow water equations? These are solutions of the linearized shallow water equations, this time with rotation, with Coriolis, on the Arakawa grids. So I'm solving the numerical solutions on the A, B and C grids. I'm starting from initial conditions which consist of 0 velocity everywhere, 0 h prime everywhere except in one grid box. So it's stationary and it's got this tower of fluid just in the middle. So the colours are showing the height anomalies, and you'll also see vectors when I start the simulations. So what happens if you use an A grid? You get, the initial fluid all in this tower does spread out, but it doesn't go to the next grid box. This grid box here, these 4 grid boxes surrounding the centre, never get any height anomalies in them. They get velocity anomalies, but there's never any velocity here, and there's never any velocity here. So there's this checkerboard pattern with only, in fact, there's only ever non-zero height in a quarter of the grid boxes, non-zero velocity in another quarter of the grid boxes. So it's very unrealistic. Does the B grid do any better? So what happens for the B grid? So this does look better. We've now got non-zero height happening in a half the grid boxes instead of a quarter. But the height only spreads out in the diagonal direction. The non-zero height never goes in horizontally or vertically, or in the x direction or the y direction. So it looks a bit better, but it still looks very unrealistic. If we use a C grid where everything is staggered, we get something much more like what we'd expect. So the height spreads out evenly across, it uses all grid boxes, and the velocity as well is at some point non-zero everywhere. So this looks like something that's much more approaching a realistic simulation. So a discussion question, something we'll discuss further in class. For solving the 2D linearized shallow water equations with rotation, what are the advantages and disadvantages of these different grids? So for this setup, the C grid looks best, but that might not always be the case, depending on, for example, how strong the Coriolis is. So these advantages and disadvantages might depend on which terms are large in the equations, which balances between terms are large, and which balances you want to represent accurately, and also might depend on other aspects of your numerical model. That's something that we'll discuss in class.